press your hand against a steel plate, solid, heavy, immovable. That steel feels like the definition of substance, like matter you can trust. But here's what nobody tells you about that plate. If you could shrink down and see what's really there at the atomic level, you'd find mostly nothing. Not air, not gas, actual emptiness. The kind of void that makes up 99.999999996% of every atom. In that steel. If an iron atom was a football field, the nucleus would be a poppy seed on the 50-yard line. Everything else? Empty space stretching to the walls. And yet, when a bullet moving at 800 meters per second slams into that plate, the steel stops it cold. No penetration. The projectile crumples or shatters. How does mostly nothing stop a piece of lead and copper traveling faster than sound? The answer sits in the strangest corner of physics, in forces you can't see, in rules written by quantum mechanics that make zero intuitive sense but govern everything solid you've ever touched. Steel can stop a bullet, not despite being empty, but because of what fills that emptiness. Electromagnetic fields, electron clouds that refuse to overlap. A principle discovered in 1925 that explains why your hand doesn't fall through the table and why armor works at all. Pulling from deep condensed matter physics research that tracks electron behavior under compression and ballistic impact. These aren't Wikipedia summaries. These are peer-reviewed studies on quantum degeneracy pressure, Pauli exclusion mechanics, and real-world bullet-stopping tests conducted at MIT and Rice University. Now back to the information. The kind that makes up most of the steel in body armor, or a ship hull, or a safe door. That atom has a nucleus, 26 protons, 30 neutrons typically, all packed into a core that measures roughly 1 femtometer across. That's 10 to the negative 15 meters, 1 quadrillionth of a meter. If you tried to express how small that is using everyday objects, you'd run out of metaphors fast. The nucleus contains more than 99.9% of the atom's mass. Protons and neutrons are dense. A single cubic centimeter of nuclear material, if you could somehow collect it, would weigh about 100 trillion grams. That's the mass of 1 billion cars compressed into a sugar cube. But the nucleus only occupies a tiny fraction of the atom's volume. The rest of the atom, the part that defines its size, is the electron cloud. And that cloud is mostly empty space. That means the nucleus occupies roughly 1 trillionth of the atom's volume. The electron cloud, which defines the atom's size, is essentially void with a few electrons zipping around at impossible speeds. 26 electrons for iron. Each electron weighs almost 2,000 times less than a proton. The mass is in the nucleus, the volume is in the cloud, and the cloud is empty. Ernest Rutherford proved it in 1911. He fired alpha particles, helium nuclei, at a thin gold foil. Most particles passed straight through, no deflection. That told him atoms were mostly empty space. But some particles bounced back at sharp angles. That told him there was a tiny dense core, the nucleus, with a positive charge strong enough to repel the positively charged alpha particles. The plum pudding model, which imagined electrons scattered evenly through a sphere of positive charge, died that day. The nuclear atom was born, nucleus in the center, electrons in orbit, vast emptiness in between, and more specifically, a quantum mechanical rule called the Pauli Exclusion Principle. Particles with the same charge repel. Electrons are negatively charged, protons are positively charged. In an atom, the negatively charged electrons are attracted to the positively charged nucleus. That attraction keeps the electrons bound to the atom. The electrons don't spiral into the nucleus because quantum mechanics forbids it, but that's another story. The key point is that electromagnetic attraction holds the atom together. Now consider what happens when two atoms get close. Say 2 iron atoms and a piece of steel. Each atom has a nucleus surrounded by an electron cloud. As the atoms approach, their electron clouds start to overlap. Both clouds are negatively charged. Electrons repel other electrons. That repulsion creates a force pushing the atoms apart. The closer the atoms get, the stronger the repulsion. At a certain distance, the repulsion balances the attraction between the nuclei and the electron clouds, and the atoms settle into a stable arrangement. That's the lattice structure of the metal. Atoms packed together, but not touching, held in place by a balance of electromagnetic forces. The electron clouds could overlap more. The atoms could pack tighter. There's another force, a quantum mechanical effect, that creates an additional resistance to compression. That's where the Pauli Exclusion Principle comes in. The principle states that no 2 identical fermions can occupy the same quantum state simultaneously. Fermions are particles with half-integer spin. Electrons, protons, neutrons, quarks, all fermions. Bosons, particles with integer spin like photons, don't follow this rule. But electrons do, and electrons are what make up the outer structure of atoms. Each orbital is defined by 4 quantum numbers. Principal quantum number, which corresponds to the energy level, azimuthal quantum number, which describes the shape of the orbital, magnetic quantum number, which describes the orientation, and spin quantum number, which is either plus 1/2 or minus 1/2. For 2 electrons to be in the same quantum state, all 4 numbers would have to match. The Pauli principle says that's impossible. In practice, this means that each orbital can hold at most 2 electrons, and those 2 electrons must have opposite spins. One spin up, one spin down. If you try to add a third electron to that orbital, it can't fit. It has to go into a higher energy orbital. As you add more electrons to an atom, they fill up the available orbitals from lowest energy to highest. The structure of the periodic table, the arrangement of elements, is a direct consequence of the Pauli Exclusion Principle. Helium has 2 electrons in the first orbital. Lithium has 3 electrons. So the third one goes into the second energy level, and so on. In a piece of steel, you have trillions upon trillions of iron atoms packed together in a crystal lattice. Each atom has 26 electrons. Those electrons are not isolated. They interact. In a metal, the outer electrons become delocalized. They're no longer bound to a single atom. They form what's called an electron gas, a sea of free electrons that move through the lattice. This electron gas is what makes metals good conductors of electricity and heat. All the states above the Fermi energy are empty. This creates what's known as electron degeneracy pressure. But the Pauli principle says they can't all occupy the same low energy states. As the volume decreases, more and more electrons are pushed into higher energy states. Higher energy means higher momentum. Higher momentum means the electrons are moving faster. That motion creates a pressure resisting further compression. A white dwarf is the remnant of a star after it's exhausted its nuclear fuel. It's incredibly dense. A teaspoon of white dwarf material would weigh about 5 tons on Earth. The atoms are crushed so tightly that the electron clouds overlap completely. The electrons are stripped from their nuclei and form a degenerate electron gas. The pressure from that gas, purely a quantum mechanical effect, is what holds the star up. Without it, the white dwarf would collapse into a neutron star or a black hole. You're trying to force electrons into quantum states that are already occupied. And quantum mechanics says no. Some goes into deforming the steel. Some converts to heat, some converts to sound. The question is whether the steel can absorb and redistribute that energy fast enough to stop the bullet. The negatively charged electron clouds push back against each other. Second, degeneracy pressure. The electrons resist being compressed into the same quantum states. Both forces work together to resist the bullet's penetration. The center. This structure is not as densely packed as a face-centered cubic lattice, which is what iron becomes at high temperatures or in certain alloys. The body-centered cubic structure has certain slip planes, directions along which atoms can slide past each other more easily. When steel deforms under impact, dislocations, defects in the crystal lattice move along these slip planes. The movement of dislocations absorbs energy. It's how the steel deforms plastically instead of just elastically. But under ballistic impact, the deformation mechanisms are different. The researchers concluded that the energy absorption depends on the balance between deviatoric stress, which causes shear deformation, and volumetric stress, which causes compression. In nanocrystalline steel, the grain boundaries restrict dislocation motion, reducing this material's ability to deform plastically and absorb energy. Stopping a bullet is not just about hardness, it's about energy absorption. The steel has to absorb the bullet's kinetic energy by deforming. If the steel is too hard, too brittle, it won't deform enough. The bullet will crack the steel and push through. If the steel is too soft, it will deform too much and the bullet will penetrate. The ideal steel for armor has a balance: high strength to resist initial penetration, high toughness to absorb energy through plastic deformation, and a microstructure that encourages energy dissipation through mechanisms like dislocation motion and phase transformations. These elements modify the crystal structure and the mechanical properties. They increase the yield strength, the point at which the steel starts to deform plastically. They increase the fracture toughness, the resistance to crack propagation. They control the transition temperature, the temperature at which steel changes from ductile to brittle behavior. The atoms don't have enough thermal energy to move easily. Dislocations can't glide along slip planes. Instead of deforming plastically, the steel fractures along crystallographic planes. This is called cleavage fracture. It's fast and catastrophic. The Titanic's hull steel failed this way. It was brittle at the cold North Atlantic temperatures, and when the ship hit the iceberg, the steel cracked instead of deforming. Modern ship steel has a much lower transition temperature, so it stays ductile even in cold water. At these strain rates, thermal activation processes, the movement of atoms aided by thermal vibrations, become less important. Dislocation drag, the resistance to moving dislocations at high speeds, becomes the dominant factor. Studies using molecular dynamics simulations, published in high strain rate journals, show that at strain rates above 10 to the 6th per second, steel's flow stress increases dramatically. The material effectively becomes stronger because there's no time for the usual deformation mechanisms to operate. Not because the atoms are solid in any classical sense, but because the electron clouds, those diffuse probability distributions of negatively charged particles, refuse to overlap. They push back with electromagnetic force. They push back with quantum mechanical pressure. The bullet's kinetic energy gets absorbed. The steel deforms. The bullet stops. The electron clouds that stop the bullet are not barriers in the way we think of walls or shields. They're not surfaces. They're regions of space where there's a high probability of finding an electron. If you could somehow watch a single electron in steel, you'd see it blur between positions. You'd never pin down its exact location. Quantum mechanics says electrons don't have exact positions. They have wave functions, mathematical descriptions of where they might be found. When two atoms get close, their wave functions overlap. The Pauli principle says the total wave function must be antisymmetric. That means if you swap the two electrons, the wave function changes sign. And the only way that works, mathematically, is if the electrons avoid being in the same place at the same time. That avoidance creates the repulsion. It's not a force in the Newtonian sense. It's a constraint imposed by quantum mechanics, a rule that says certain configurations of particles are forbidden. But because the Pauli principle creates an effective force pushing them apart. The electromagnetic force provides the attraction and repulsion between charges. The Pauli principle provides the additional resistance to compression. Together, they create the sensation of solidity, the illusion that matter is something you can lean on. The electrons are even tinier. The space between them is void. If you could remove all the empty space from the atoms in a human body, the actual matter would collapse down to the size of a grain of dust, all the protons, neutrons, and electrons. That grain of dust would weigh the same as the human, about 70 kilograms, but it would fit on the head of a pin. And yet, that grain of dust would be incredibly dense, nuclear density, the kind of density you find in neutron stars, because all the empty space would be gone. A steel plate is as thick as it is because the atoms are as big as they are, and the atoms are as big as they are because of quantum mechanics. When two hydrogen atoms combine to form a hydrogen molecule, it's because the electrons can lower their energy by sharing space between the two nuclei. But they can't occupy the same quantum state, so they pair up with opposite spins. That's a chemical bond. When carbon atoms arrange themselves into diamond, one of the hardest materials known, it's because the electron orbitals overlap in a specific way that creates strong directional bonds. The Pauli principle dictates which orbitals can be filled and how the atoms can arrange themselves. When a bullet hits Kevlar, the fibers stretch and the polymer chains slide past each other, absorbing energy. The Pauli principle governs the strength of the covalent bonds. The electromagnetic force governs the hydrogen bonds. Together, they give Kevlar its ability to stop bullets without the weight and rigidity of steel. When a bullet hits ceramic, the ceramic doesn't deform much. Instead, it shatters. But in shattering, it absorbs a huge amount of energy. The bullet's tip is eroded by the hard ceramic fragments. The ceramic creates a cone-shaped crack, and the bullet has to push through all that fractured material. Behind the ceramic is usually a backing layer of Kevlar or steel to catch the remaining fragments. The ceramic's hardness comes from its crystal structure and the strength of its ionic or covalent bonds. Again, electromagnetic forces and quantum mechanics. The electromagnetic force and the Pauli Exclusion Principle, forces that operate on a scale trillions of times smaller than the bullet. Forces that you can't see or feel directly, but forces that are real and measurable and absolutely critical to the world we live in. They mixed multi-walled carbon nanotubes with Kevlar nanofibers. The resulting nanofiber mats were superior at stopping high-speed projectiles compared to steel plates and regular Kevlar. The reason comes down to energy dissipation at the nanoscale. The carbon nanotubes, cylindrical structures just one atom thick in each layer, have incredible tensile strength because of their strong carbon-carbon bonds. When a projectile hits the nanofiber mat, the nanotubes absorb energy by stretching and by breaking bonds. The energy dissipation happens over a very short distance in time, which is ideal for stopping fast-moving projectiles. But even these advanced materials rely on the same fundamental physics. Electromagnetic forces between atoms, the Pauli Exclusion Principle preventing electron overlap, quantum mechanics dictating how matter behaves under stress. The researchers used a modified split Hopkinson pressure bar to test the materials. They fired tiny projectiles at supersonic speeds and measured the energy absorbed. The nanofiber mats outperformed steel by a significant margin, all because of carefully engineered atomic structure. The electron clouds, diffuse and probabilistic, create electromagnetic fields that repel other electron clouds. The Pauli principle, a rule of quantum mechanics, prevents electrons from occupying the same state. These forces combine to give steel its stiffness, its resistance to compression, its ability to absorb energy. When a bullet hits, the steel pushes back, not because it's solid in any intuitive sense, but because quantum mechanics makes it solid. And yet those forces scale up. They compound. Trillions of atoms working together create macroscopic properties: strength, hardness, elasticity, toughness. Quantum mechanical principles that create an effective resistance to penetration. The emptiness is real, the solidity is real, both can be true at the same time. That's quantum mechanics. That's the energy of the highest occupied electron state. The pressure comes from the fact that electrons with high momentum, high energy states, are moving fast. And when they bounce off boundaries or scatter off lattice vibrations, they transfer momentum. That momentum transfer creates pressure. In white dwarfs, where densities reach millions of times normal matter, the degeneracy pressure can reach 10 to the 22 pascals. In steel, it's much lower, but still significant enough to contribute to the material's bulk modulus, its resistance to compression. So it takes roughly 1.7 million atmospheres of pressure to compress iron by just 1%. That resistance comes from both the electromagnetic repulsion between atoms and the quantum mechanical degeneracy pressure. When a bullet hits steel, it's trying to compress the material locally. The compression wave propagates outward from the impact point at the speed of sound in steel, about 5,000 meters per second. The atoms are pushed together, their electron clouds overlap more, the electromagnetic forces push back, the degeneracy pressure pushes back, and the steel resists. The kinetic energy is 1/2 times mass times velocity squared. That's about 490 joules. A rifle bullet has much more energy. A 7.62 millimeter NATO round has a mass of about 10 grams and a velocity of about 800 meters per second. That's 3,200 joules. The steel has to absorb all that energy to stop the bullet. Elastic deformation stores energy temporarily. When you compress a spring, you store elastic energy. When you release the spring, the energy comes back. Steel does the same thing, but on a much smaller scale. The atomic bonds stretch and compress. Energy is stored in the electromagnetic fields between atoms. When the compression wave passes, the bonds return to their original length and the energy is released. But elastic deformation alone can't stop a bullet. The amount of energy that can be stored elastically is limited by the yield strength of the material. Once the stress exceeds the yield strength, plastic deformation begins. This happens through the movement of dislocations, line defects in the crystal lattice. A dislocation is a region where the regular arrangement of atoms is disrupted. When a shear stress is applied, the dislocation can move through the lattice. As it moves, atoms on one side of the slip plane shift relative to atoms on the other side. This is how metals deform plastically, and it's how they absorb energy. Moving a dislocation requires energy. That energy comes from the bullet's kinetic energy. The more dislocations that move, the more energy is absorbed. To the 12th per square centimeter. More dislocations mean more obstacles to dislocation motion. This is why cold, worked steel is stronger but less ductile than annealed steel. For ballistic applications, you want a balance. High enough strength to resist initial penetration, high enough ductility to absorb energy through plastic deformation. When steel is deformed very rapidly, there's no time for heat to dissipate. The energy from plastic deformation converts to heat locally. The temperature rises. The hot region becomes softer, easier to deform. More deformation concentrates in that region. The temperature rises further. This creates a positive feedback loop. A narrow band of highly deformed hot material forms. This is an adiabatic shear band. It's a localized failure mode that can occur in armor steel when a bullet impacts. The shear bands are typically 10 to 100 micrometers wide. The material inside the band is severely deformed and heated. In some cases, the temperature can reach the melting point locally. The microstructure inside the band is drastically different from the surrounding material. Fine grains, sometimes nanocrystalline, high dislocation density. In extreme cases, phase transformations. For armor steel, adiabatic shear banding is usually undesirable. It represents a localized failure mode. If a shear band forms and propagates through the steel, the bullet can penetrate. Steel manufacturers work to suppress shear band formation. They do this by controlling the microstructure, fine grain sizes, uniform distribution of alloying elements, avoiding inclusions and voids that can act as stress concentrators. The goal is to spread the deformation uniformly through the material rather than concentrating it in a narrow band. The impact face needs high hardness to erode the bullet. The interior needs high energy absorption. The back face needs high ductility to prevent spalling, the ejection of fragments from the back surface. By grading the microstructure, you can optimize each region for its specific function. The researchers fabricated steel plates with controlled microstructure gradients using selective laser melting. They tested the plates against ballistic impacts. The graded plates showed up to 30% improvement in energy absorption compared to homogeneous plates of the same average grain size. The improvement came from the fact that the graded structure forced the deformation to spread through a larger volume of material, rather than concentrating at a single depth. Individual atoms. The researchers showed that by tuning quantum parameters, they could make electrons transition between solid and liquid phases. This work is foundational for future quantum technologies, including quantum computing and advanced superconductors. It's also another example of how quantum mechanics governs the behavior of matter at the most fundamental level. The study, published November 6, 2025, used state-of-the-art tensor network calculations and exact diagonalization techniques to model the behavior of hundreds of interacting electrons. They found the Pauli Exclusion Principle plays a critical role in stabilizing the crystalline phase. The electrons can't occupy the same quantum states, so they arrange themselves in a regular lattice. It's the same principle that makes steel solid, applied to a completely different system. Quantum mechanics is universal. The rules don't change. Whether you're looking at iron atoms in a steel plate or electrons in a quantum material, the Pauli principle applies. The electromagnetic force applies. The behavior of matter follows from these fundamental laws. They're tested and verified every day. Every time you lean against a wall, every time a bridge holds a truck, every time a bullet hits armor and stops. The physics works, the math works, the predictions match reality. And at the heart of it all is this bizarre truth. Matter is mostly empty space. And yet that empty space, governed by quantum mechanics, is what makes matter solid. So the next time you look at a piece of steel, remember what it really is. Trillions of iron atoms. Each atom a tiny nucleus surrounded by a cloud of electrons. Each electron obeying the Pauli Exclusion Principle. Each atom interacting with its neighbors through electromagnetic forces. All of it arranged in a crystal lattice, with atoms spaced just right to balance attraction and repulsion. And in that balance, in that empty space filled with quantum mechanical rules, steel finds its strength, its ability to resist, its capacity to stop a bullet, not by being solid in the way we imagine solid, but by being a quantum mechanical structure that refuses to be compressed. That's the real reason steel works. That's the real reason anything solid works. Quantum mechanics in action. In 1925, Wolfgang Pauli wrote down a simple principle. No two fermions can occupy the same quantum state. He probably didn't imagine that this principle would explain not just the structure of the periodic table, but the solidity of matter itself. The reason you don't fall through the floor. The reason steel can stop a bullet. But that's exactly what it explains. Pauli's principle, combined with electromagnetic forces, creates an effective barrier, not a physical barrier, a quantum mechanical one. That barrier is strong enough to hold up buildings, stop bullets, and make the world we experience feel solid and real. What matters are the forces in that emptiness, the rules governing the particles, the quantum mechanics that turn nothing into something, turn void into structure, turn space into steel. Topics included superconductors, quantum information systems, nanoelectronics, all of it rooted in the same principles. Quantum mechanics, electromagnetic forces, the Pauli Exclusion Principle. These aren't just academic curiosities. They're the foundation of modern technology. And they're the reason materials behave the way they do. Because electrons follow rules written in the math of quantum mechanics. Because the empty space inside every atom is not really empty at all. It's filled with fields, with forces, with constraints that make matter matter. And when those constraints are challenged, when a bullet tries to force its way through, the atoms push back. The electrons push back, the quantum mechanics push back, and the bullet stops. Not steel's density, not its hardness, its quantum mechanical structure, the forces operating at scales you can't see, forces that are real and powerful and absolutely fundamental to why anything in the universe is solid. Empty space that isn't empty. That's the secret. That's the answer. That's why steel can stop a bullet.